In this video, we want to take a look at the notion of projection. And that notion is this. I've got a couple of vectors here, u and v. And what I want to do is I want to project u onto v. Now I could do this in many ways, but in particular, I want to do it perpendicularly. So write them both with the common starting point here. And then the end point of u, I'm going to drop a perpendicular down here to v. Now, I'm looking for this vector right here now. So it's in the same direction as v. So I'm just going to have to figure out what number do I have to multiply v by in order to scale it to be just exactly that vector. This vector has various things that it's called. It is sometimes called the component of u in the direction of v. It's sometimes called the vector projection of u onto v. We will use both of those terms. One of the things that when I think about projections, there's a formula, and I'm not a big fan of memorizing things, so I don't really memorize the formula, but I know how to figure it out because I know my trig. I know that if I've got this angle theta in here, and I know u, this is a right triangle, so I can use trig to find out how long this side is here. And the length of that side is what's called the scalar projection. Now, so my trig is saying I'm looking for what would be the adjacent side to that angle, and I know the hypotenuse. So adjacent and hypotenuse, that would be cosine. So I know from my trig that the cosine of the angle theta is the length that I want divided by the length of the hypotenuse. So in particular, what I want is the length of the hypotenuse times the cosine of the angle. This is what's called the scalar projection. I have the formula for it right here. The scalar projection of u onto v is the length of u times the cosine of the angle in between them. Now, I need to be able to calculate that because I can't always just measure the angle. And so I know that length times cosine, that's closely related to the dot product. So I've got this, I know that the dot product of u and v is the length of one times the length of the other. There's a lot of vertical lines there, times the cosine of the angle in between them. And so if I want just the length of u times the cosine, then this has got to be divided over to the other side, and that's exactly what I have here. The dot product divided by the length of v is going to be the length of u times the cosine of theta, which is the scalar projection of u onto v. Okay. Now, I need to turn that into a vector because this is just a number. This is the length, right? I mean, the dot product gives you a number. The length of a vector gives you a number. You divide two numbers, it's just a number. That's not a vector. So that's what's called the scalar projection. I now need to turn that into vector projection. Now, the process that I'm about to do is one that I do quite often when I'm trying to create a vector that does a particular thing, that points in a particular direction and has a particular length, right? And so I know what direction I want this to go in. I want it to go in the direction of v. And I know how long I want it to be, that is this. Now, I can't just say multiply v by this because v is already pretty long, or maybe it's really short. I don't know. I don't really know how long v is, but I know how long I want to have it end up. So what I can do is I can scale v down to being a unit vector and then multiply by the length that I want. So v going down to a unit vector would be v divided by the length of v. That's a unit vector. And now if I multiply that by this right here, u dotted with v over the length of v, I will have produced a vector that's parallel to v, right, because it's a scalar multiple of v, and it is of length exactly equal to what I want. I take the vector that I know I want the direction to be, divide by its length, so now I have a unit vector in the right direction, and then multiply by the length that I actually want, and I generate the vector that I actually want. This is what's called now the vector projection, and the notation is, we write it like function notation, where the function name is projection onto v, and what are you projecting onto v? You're projecting the vector u, okay? And so this formula right here is the one that I just wrote down there. It's the length that I want times the unit vector in the direction I want. And then doing a little bit of, just moving stuff around here, a little bit of algebra. So the denominator's got those two lengths of v, so I got a length of v squared. But then I realized, oh, the length of v squared could just be done with the dot product of v with itself. So the vector projection is the dot product of u and v divided by the dot product of v with itself times v. So this is the projection of u onto v. That's giving me this vector right there. Now, let's do an example. Here's two vectors. I apparently didn't turn that into looking like a vector u, so this is supposed to be u. It's 3, 4, and the vector v is 2, 1. Now the scalar projection of u onto v, that's just this formula that I used right here. It's the dot product divided by the length of the one you're projecting onto. So the dot product is 3 times 2 is 6, 4 times 1 is 4, add those together, and the length of v on the bottom is 2 squared plus 1 squared under the square root. So we got 10 over the square root of 5, which is 2 root 5. Now, that's just the length that I need. The actual projection of u onto v is, and I'll use this formula here now. So the dot product is still 6 plus 4, and now the v dotted with itself is 4 plus 1, right? 2 times 2, 1 times 1. And this is 10 over 5, which is just 2. And I multiply times the vector v, and I end up with 4, 2. So the vector projection of u onto v is 4, 2. Before I do the next calculation here, I want to scroll down here and actually look at the picture. I have the vectors drawn here. 3, 4, this one is the vector u right here, and 2, 1, that's the vector v down there. And actually you can see that projecting u onto v in this case, different than the picture I drew above, u is so long that when you project it down, you have to extend v out, right? So v has to get longer in order to be the projection, starting here and ending out there. Well, we calculated that it's actually twice as long. I had to take a 2 right here and multiply it by u. Look at that from the point of view of length as well. We determined in this step right here that we wanted a length of 2 radical 5, but the vector v itself has only length radical 5, so we had to double it. We had to double it in length in order to get the length we needed. So that would be the projection of u onto v. Now, I could actually do it the other way too. I could say, no, I want to project v onto u. So I would be going from here, dropping a perpendicular down to v, perpendicular down to u, and looking for this vector now. Right? So this just interchanges the roles of u and v. So rather than before I had the dot product divided by v for the scalar projection, because I was projecting onto v, now that I'm projecting onto u, I have the dot product times or divided by the length of u. And in this case, it is actually 2, right? Because this is, the dot product is still 10, but the length of u now is 3 squared plus 4 squared, square root, so that's the square root of 25. That's 5. This is 2. So the length that I want here is 2, so I have to scale u down to have length 2. Well, what is the length of u? The length of u is 5, so I'm going to have to scale 5 down to get to 2. Anyway, here's the calculation. Notice that the denominator here is not v dotted with v, it's u dotted with u because I'm projecting onto u, and the vector I'm multiplying out here is not v, it's u because I'm projecting onto u. And so this formula changed a little bit because I interchanged the role of u and v. The numerator didn't change because the dot product's commutative, right? It doesn't matter if you do v dotted with u or u dotted with v. Anyway, dot product is still 10. The denominator u dotted with u is 25. So this is 2/5. Notice I'm dividing by 5, which is the length of u, and I'm multiplying by 2 so that I get something of length 2. But since it's in the direction of 3, 4. Anyway, 2/5 multiplied by that is 6/5, 8/5. Right, so that vector right there, 6/5 in the x direction, 8/5 in the y direction. Oh, one thing I want to say about this. I've seen many times students just try to memorize formulas. And so they have, this formula right here memorized. The projection is that. And then they don't pay at all attention as to what question is being asked, right? On a quiz or a test, I'm going to say, hey, here's the vector u and here's the vector v. Project v onto u. And they use this formula because it's, this is the projection formula. Well, it's the projection formula for u onto v, right? If you're doing v onto u, you got to do this. You got to think about what vector you're projecting onto. Then you know that the answer should be a scalar multiple of that vector. So if I'm projecting onto u and I'm multiplying by the vector v, that can't be right. That can't be right because that's going to be in the direction of v. So just pay attention to what it is you're actually doing. Okay. Now here's a standard problem relating to projections, and that is to break a vector up into parts where one part is parallel to another vector and the second part is perpendicular to that vector. So in particular, I'm thinking about a physics problem here. So you got a ramp and you got some object sitting on the ramp, right? Gravity is pulling straight down, but the object can't go straight down because the ramp is in the way, the ground is in the way. So it's going to move that way, right? So the question is, how much of gravity is pulling parallel to the ramp here? And in particular, you would also need to know, both of these, that is, how much is pulling parallel to the ramp and how much is pulling perpendicular to the ramp. When you do the force analysis, of course, that this part of it, the perpendicular part, is going into friction. It's what's called the normal force, perpendicular, right? Normal force. And this is the part that would be trying to accelerate the ramp down. There's various things going on here because the part of gravity trying to accelerate it would be going this way, but then the normal force would be adding to friction, and friction would then be producing a force opposing gravity, and so you could figure out how much, based on the stickiness of the ramp, you can figure out how much friction there is, and then subtract those two vectors and see how fast it would actually accelerate down the ramp. Right? If it was a frictionless ramp, of course, that there would be no force of friction, and it would just accelerate as the parallel component of this. Okay. So here's the way we word this. If I'm given two vectors, u and v, I want to find two other vectors. I'm going to call them w1 and w2. So the w1 is parallel to v, w2 is perpendicular to v, and the sum of w1 and w2 is u. So this is u, and this is v. Then w1 is the part here that's parallel to v, and w2 is the part that's perpendicular. And that the vector u is the sum of those two. This is the parallel part parallel to v, this is the part perpendicular to v, and all of u is the sum of those two parts. We often call these the components of u in the direction of v and perpendicular to v. Right? The component of the acceleration parallel to the ramp and perpendicular to the ramp. Okay. Well, we've already solved part of this problem because W1 is just the projection of U onto V, right? So this is that right here. And then how do you get W2? Well, if I know these two, because I'm given U and I calculate W1, then W1, well, just take this thing right here, solve for W2. So bring the W1 over to the other side, W2 is U minus W1. Okay? You find the part parallel to V by doing the projection, and then you just subtract to get the perpendicular part. As an example of that, let's just use the two vectors that we had up above. I should also mention that the example up above and this example I'm working in R2, but you could as easily work in any Rn. So I want to write, in this problem, I want to write U in terms of vectors parallel to V and perpendicular to V. So that's exactly the way it was described above. So W1 is the projection, which I already calculated up above, is 4, 2, right? And then W2 is the difference of U and that projection, which is minus 1, 2. And I want to go back up and look at this picture, right? So this was the projection, moves over 4 and up 2, and then the W2 is this one right here, which is backing up 1 and going up 2. So there is indeed the minus 1, 2. Negative 1 in the x direction, plus 2 in the y direction. Okay. And those are perpendicular to each other. U is the sum of the projection and that other one over there. Now what if I went the other way? What if I wanted to do V in terms of U, right? Parallel and perpendicular to U. So this one would be the W1 and this one would be the W2. Right? So that the vector, because V, it's all covered up at the moment here, but V was really short, right? We had to extend it to get to that. So V was this short thing there. The W1 and W2 look like that. In this case, so now I'm going to find the components of V parallel and perpendicular to U. So the parallel part is projecting U, my editor again. This is projecting V. Where's my pencil? This is projecting V onto U. And we did that in the calculation above, 6/5, 8/5. And so then my editor, yes, that's a V. So W2 then is V minus U1. So 2, 1 minus that, which is 4/5, negative 3/5. And does that jive with the picture? So I'm moving positive in the x and negative in the y. And I think that does, because I'm moving positive in the x direction and negative in the y direction to get that vector going down there. Okay. This comes up in all kinds of places when you need to take a force, a vector of some kind, and split it up into two components. One parallel to a known direction, one perpendicular to a known direction, and then use those different components for whatever the problem is using them for. So anyway, there's projections. They definitely use dot products. Have fun working on the problems.